We can break an awful lot of logic down to three basic truth tables. And I'm going to show you those three tables. We already saw them in the previous clip. In this clip, we're going to symbolize them. So this statement, first statement is P and Q. Remember, the basic example is ice cream and $1 million. So P stands for you get the ice cream, Q stands for you get the $1 million. Remember that our possible truth values are that P can be true and so can Q. P can be true, Q false, false true, false false. To do a truth table for and, if P stands for one proposition and Q for another, and it doesn't matter whether it's ice cream and $1 million or green cheese and a cow jumped over the moon. Makes no difference what the statements are. If our logic is to be consistent, we have to have the same result anytime we have two propositions connected with an and. Okay, so if we have P and Q, and if P and Q are both true, then certainly we say that the and statement is true. In any other case, we have to say that they're not both true, so that the and can't be true. I'm going to put a circle around this value to show that the exceptional value, the value that is an exception to the others, for the and statement is the case where both conditions are true and we get what we call, we get a true statement. Okay, now P or Q. Notice that we had a symbol for and. We have P and Q, and this up arrow, this little caret here, means and. We come down here and we have P or Q, and we're going to use an inverted caret for or. So we have P, we have Q. The truth values are as follows, or are as listed. Now we want or. The exceptional case for or is where both the conditions are false. If P is not true and Q is not true, then P or Q certainly isn't true. In any other case, we're going to say P or Q is true. Now this can sometimes be a little bit confusing because you say, well, it says or, and if they're both true, is that really true that one or the other is true? That's because the word or gets used somewhat ambiguously in our language. In some contexts you'd say, yeah, that should be true, and in some contexts you might say it's false. Like if a mother says to a child, either you get in here or something terrible is going to happen, then that's what we call an exclusive or. You're going to do one or the other. If one happens, the other isn't going to happen. But if we say, well, no, I'm not going to use an example here, but we can say, make a lot of statements where or really means as long as they're not both false. And this is the logical or that we're using. The other is called an exclusive or, where we exclude the case where these things are both true, and we'll see a little bit about that later. But the rule that we're going to use in logic is this or means this kind of an or, where unless both conditions are false, the or statement is true. And then we have the statement if P then Q, which is symbolized by an arrow. Now this arrow is really made out of a dash and a greater than sign, but it's really supposed to be just a plain old arrow. That's a conditional symbol. Means if P then Q. So if the statement is if P then Q, this means Q follows from P. Now if we write our truth values again, remember what we said before. This says if P is true, then Q has to be true. Now if P happens to be false, then we can't test the condition to see whether it's true or false. We're just going to call it true. That's going to be taken as a true statement. And if P is true and Q is true, well, that's what we would say is the true. The one exceptional statement is where P is true and Q is false, because this says if P, then Q. If P is true, then Q is true. Here we got a case where P is true and Q isn't, and that is clearly the case that we're going to want to single out, just like we singled out the case on the OR where both are false. Now we can combine statements to make what's called compound statements. So we're going to take a look at one compound statement. Let me just fix a little smudge of the pen here. To make that look right. Let's just evaluate this compound statement, and let's see how this works. Now we're going to do some of these in more detail, but right now we're just going to do this one with the same usual values of P and Q. Now this statement says not P and P or Q. What that means in a given context, maybe it says you're not going to get the ice cream and you're going to get the ice cream or the $1 million. Would you be happy if that was the case? Think about that. Okay, in any case, if P is true, then not P is false, right? And if P is true, again, not P is false. So in this line, P is true, so not P is false. In this line, P is true, not P is false. In this line, P is false, so not P is true. And again, P is false, so not P is true. Now the next line we want to evaluate is P or Q. Well, remember that the OR is true unless both P and Q are false. So we have the exceptional case here, and otherwise the statement has to be true. Now what we want to evaluate is the whole statement. Well, if we look at it here, we see that we have not P and P or Q. To evaluate this statement, we have an AND connecting the not P, which is given in this column, and the P or Q, which is given in this column. When we have an AND between two statements, then both this and this have to be true, or the whole statement is false. Now in the first line, we see that not P is false, P or Q is true. If we have an AND between those, that's going to make the statement false. And here again, we have a false and a true. Again, that makes it false. Now here we have a true and a true. The not P is true and the P or Q is true. Well, that makes the combined AND of this statement true. Here we have a true and a false. Since it's an AND statement, again, we have a false. Now, if you didn't catch that and you didn't really understand it, we're going to do several examples of this sort of thing. But what you see here is how we set up a truth table. We note that we have an AND between two statements, a not P and a P or Q statement. So we evaluate those two statements that are connected by the AND. Then we can evaluate the AND.